So where we left off last time was in how to determine salinity. So now we can compare whether something's salty or fresh. Well, besides just salinity, how do fresh and salt water vary? For the most part, they're pretty much very similar. If you just look at seawater or look at fresh water, they're both kind of a clear blue-green color. That's because light transmission doesn't vary that much that you could see it with the naked eye. Other ways they vary. Just going to the beach, you know that salt water has a particular odor. And you've probably gone swimming, you've tasted that seawater tastes salty. Freshwater doesn't have any of those. There's also a couple other properties that are a little harder to tell right off the bat. First of all, they have a different pH. We're going to spend a lot of time talking about that later on. But basically, pure water is neutral, 7.0 on the pH scale, while seawater is slightly basic or alkaline. Their densities at their maximum are different. Pure water is 1 gram per centimeter cubed. Seawater is a little bit more, and that should say 1.028 grams per centimeter cubed. Freezing points and boiling point are kind of important. These are both called colligative properties, and as you may or may not remember from chemistry, a colligative property is one based on the amount of the dissolved particles and not particularly based on what the particles are. So just by adding a dissolved substance to water, you change its freezing point. And at typical amounts of seawater, 3.5% or 35 parts per thousand, the freezing point actually goes down to negative 1.9 degrees Celsius. That's when seawater begins to freeze. And the same thing happens with boiling point. If you add salt to water, you actually raise the temperature slightly, 100.6 degrees. People utilize this when they make pasta. You salt the water for pasta. It makes the water boil at a slightly hotter temperature, which actually allows the pasta to cook slightly faster. So how does salinity vary around the world? Well, typically in the open ocean, the salinity is anywhere from 32, 33 to about 38 parts per thousand. The average being about 35 parts per thousand. That's typically what we see around here in the Atlantic. Some seas are more brackish, like the Baltic. Red Sea is fairly salty at 42 parts per thousand. Then you get to the hyper saline, really extreme salinities like you see in the Great Salt Lake and the Dead Sea. Dead Sea is so salty that you can actually float a beach chair in it and sit right on it. 330 parts per thousand. We like to think of our tap water and our bottled water as being pure, but it's really has a very small amount of salt in it. If you have water that is completely pure, it tastes kind of flat. And salinity varies. So what does this mean? It means that there's something going on that's changing salinity. And there's processes that decrease salinity and some that increase salinity. So there's a big table in your book. It's table 5-5 if you want to look at it. But they go through each one and kind of go into greater detail than we do. What you do need to know is that the things that decrease salinity tend to be precipitation, runoff from land, melting of icebergs, and melting of sea ice. Now, how do these change salinity? They don't actually change the amount of salt present at all. What they do is all four of those add water to the ocean, or to the surface of the ocean. And by doing that, they change the ratio. Remember, salinity is the ratio of dissolved salts to parts per water. So by increasing the water, you're changing the salinity. Now, please note that this says melting sea ice and not melting glaciers. They're not the same thing. Same thing with icebergs. All right, so the things that increase salinity tend to be evaporation. If it's very hot or there's a lot of wind blowing across the surface of the ocean, that will cause water to evaporate from the surface, leaving the salt behind. The same thing happens with sea ice. We mentioned this slightly when we talked about why does ice float. But when sea ice forms, its salinity is significantly less than that of the surrounding water, and that means that all that excess salt is expelled. So when it initially freezes, it's around 10 parts per thousand. Over time, the salt leaches out of the sea ice. After about a year, sea ice is basically pure, and there's all the salt gets expelled back into the water. But if you think about these processes, these don't all happen everywhere on the planet in equal amounts. Evaporation tends to occur in places where it's very hot, like along the equator. Obviously, sea ice is only formed in very cold areas, like at the poles. The majority of precipitation on this planet tends to occur in the middle latitudes, like we live in the 30s and 40s in terms of latitude. So you're going to see that this is one of the reasons why we've been working on the lab, where you can see that salinity varies greatly depending where you are on the planet. In order to talk more about how salinity varies, we need to just do a quick refresher on the hydrologic cycle and where oceans came from. So, as you probably know, most of the water on the planet is in the ocean, 97.2% to be exact. And then we go downward with this table on the left. There's a decent amount in glaciers and ice caps, a little more than 2%. Then groundwater, which would consist of aquifers and places like that. Very, very small amount in streams and lakes, which seems a little counterintuitive. We see a lot of streams and lakes, but actually very small amount compared to the overall. And then a tiny fraction of the water on the planet is in the atmosphere. So if we're going to talk about the hydrological cycle, we need to talk about where the water came from. So there are two main theories about the origin of water. The first theory that came about was outgassing from volcanoes, which basically meant when our planet was newish at around 3.8 billion years old, there was a lot of volcanic activity and the planet began to cool, and it gave off a lot of volcanic explosions. And with this came steam, and that this steam cooled and eventually ran into the oceans and made our liquid ocean. It wasn't salty at first. It was actually fresh and very, very acidic. At least that's what was believed. This kind of fell out of favor in the 70s and 80s, and if you read any older oceanography books from that time period, there was an idea that most of the water on this planet came from bombardment from comets. Comets are big icy rocks. We should see a really interesting one later this year that hit the surface of the Earth and then melted. And there's definitely some of the water that came from bombardment from comets. We can tell this by doing radiometric dating and looking at the different isotopes. But we've actually come back, and the current thinking is actually the first theory. So if you were asked on a test, the more modern explanation would be this one. We've come full circle, and we think most of the water on this planet came from outgassing. So now we've explained where the water comes from, but where does the salt come from? So salt is basically coming from two different places. The metals and some of the things like silicate come from weathering of rock. So it rains, it creates runoff, plants crack the rocks, it breaks down, it gets washed into rivers, rivers head into the ocean where it breaks down more and more. And that's where we get things like sodium, different substances like that. Chlorine, bromine, and iodine, which are the anions that are in seawater, or some of the more common ones, came primarily from the outgassing of volcanoes. HCl was a common component to be found back then, and the chlorine that's in our sea salt now, which is the primary component, came from outgassing of volcanoes. So where are these dissolved components added from? They're from streams. The most common one in streams is carbonate. We'll talk about that later on. And again, we mentioned volcanism adds some of these cations. So they're added and from streams and outgassing of volcanoes, hydrothermal vents, things like that. Salt is actually removed at almost the exact rate it's added. It's kind of a nifty little equation, primarily through biological processes or being dissolved into sediments. There's a couple pictures in your book of evaporites. Evaporites are areas where seawater is thrown up onto the surrounding area, and it makes these flat pans, cake-shaped substances that are really just salt. And some of the dissolved components from seawater go directly into the air. This can be transported all over the world. It's interesting to just take a note that the entire volume of the ocean is cycled through a hydrothermal vent every 3 million years. There's a little factoid in the book, and it's going around quite often. The last thing we're going to talk about, and we'll spend a lot of time on this in class, is residence time. Residence time is defined as the time required to completely replace, amount of a given substance in the ocean. And the formula for it is T is equal to A over R, where T is time, A is equal to amount, usually in grams. Rate is rate of removal, grams per year. And this tends to be specific to each element. Sodium has a very long residence time, whereas other metals like aluminum have very short residence times. If we have an equation, we're going to be doing problems with it. The biggest mistake kids make, and one that you're going to watch, is to make sure that your unit for amount is the same unit as the top part of rate of removal. So if you have grams in one, make sure you have grams in the other and not kilograms. You may have to do a conversion first. So that's kind of it for this video. We'll go over some of this in class.